Hi, and thanks for joining me in this video on error analysis. In this video, we're going to talk about distributions. Distributions can be categorized as either discrete or continuous. We're going to talk about both. Discrete distributions are ones which have really well-defined intervals or bins, and we count the number of items that occur in those bins, and that gives us a frequency distribution. Here's an example that we did in lab number 1, where we counted the number of days that certain temperatures occurred each year. We had bins of 10 degrees Fahrenheit, and that's what we have along the bottom. It shows the temperature in degrees Fahrenheit, and along the side it shows the count, or the number of times that those temperatures occurred. So this produces a curve with values of the variable and also frequencies of occurrence. In other words, the number of times things happened. Another example of frequency distribution that we find in atmospheric sciences is drop size distributions, measuring the size of cloud droplets and then putting them in bins to come up with some sort of distribution. Here we have a frequency distribution table of drop size diameter and the frequency of each diameter. The diameters represent bins that are approximately 2 microns in width, and the frequency is the number of times those droplets occur in that bin. We can plot that up as a frequency distribution curve. We call this a histogram when we have a discrete distribution, meaning that we have bins. Then the histogram is a graphical representation of a frequency distribution for a discrete distribution. Notice that the bin sizes, as I mentioned, are approximately 2 microns each, and the numbers, those measured diameters, are the center points for each bin. So for example, all the way on the left side, the 10 micron bin size or bin goes all the way down from 9 microns all the way up to 11, and so on and so forth. Each one of these bins is 2 microns in diameter. So if we could get an instrument that can measure even smaller and smaller sizes, that would reduce the bin size. And how about if we can measure more and more cloud droplets? Pretty soon, the bin sizes are so small and the numbers of droplets that are so big, the frequencies increase to the point where you start to see a blurring of the bins. You don't really see a discrete distribution anymore. Instead, we call this a continuous distribution. And a continuous distribution is a distribution without any bins, really. Continuous distributions are really nice because they're easy to work with. We can come up with equations that fit the curve and are easily calculatable. There are a number of known distributions, continuous distributions, such as the normal distribution or the Poisson's distribution or the binomial distribution. The theory behind continuous distributions is pretty well known, and we can use these continuous distributions and the equations to determine probabilities of occurrence. Also, it helps us with statistical tests, and we can assume a distribution is continuous if the bin sizes are very, very small and if we have a large number of measurements. Here's an example of a continuous distribution where we took the drop sizes and got rid of the bins and connected the dots. You can also determine a relative frequency distribution by taking each bin value and dividing it by the total number of measurements, and that gives you a percentage of measurements. Here's an example of a relative frequency distribution for the example that we're looking at, the drop sizes. And you can see that the relative frequency adds up to 1. In other words, we have 100% of all the droplets. This is the plot. It looks the same. The numbers are just different. And here, the numbers are just fractions, decimals. But if you multiply it by 100, that'll give you the percentage of observations or measurements in that bin. So that's a little bit about distributions. We're going to talk about how to use distributions in our next video.